Dear students, today we will start a new chapter, that is complex number. So first of all, what is a complex number? Any expression that is of the form of a plus iota b, where a, b are both real numbers and iota is an imaginary number whose value is square root of -1. Complex number is denoted by, any complex number is denoted by, complex numbers are denoted by the letter Z. So Z is equal to a plus iota b is a complex number. Any complex number that can be written in the form of a plus iota b, or the number that is of the form of a plus iota b, is known as complex number, where a and b both are real numbers and I, that is known as iota, whose value is square root of -1. For example, Z is equal to 2 plus 3 iota. This is the complex number because this is of the form of a plus iota b. Z is equal to, say this is Z1, this is Z2. Z2 is equal to 1 minus iota. This is again a complex number because this is of the form of a plus iota b, that is 1 plus minus I. So any number that is, or any expression that is of the form of a plus iota b, or any expression that can be written in the form of a plus iota b, is known as a complex number. Here Z is equal to a plus iota b is the general form of the complex number. This a is known as here the real part of complex number. Here a is known as the real part of complex number and is denoted by Re of Z. Re of Z means real part of the complex number, and this b is known as imaginary part of complex number, imaginary part, and is denoted by Im of Z, that is b. So b is imaginary part. If we take this example, that is Z1 is equal to 2 plus 3i, here the real part of the complex number is Re, real part of the complex number is 2, and imaginary part of the complex number is 3. In the same way here, the real part of the complex number is 1 and the imaginary part of the complex number is -1. So the general form of the complex number is Z is equal to a plus iota b, where a and b both are real numbers. Here the real part of the complex number is Re of Z, real part of the complex number is a, and the imaginary part of the complex number is b. So let us define another term that is related to the complex number, that is known as the conjugate of complex number. The conjugate of complex number is denoted by Z bar. That is equal to, you have to change the sign of the imaginary part. If the sign of the imaginary part is plus, then you have to put minus in conjugate. If the sign of the imaginary part is the minus, then you have to write plus in conjugate. So Z bar, that is the Z conjugate. In other words, we can say this is the mirror image of the complex number. So that is a minus iota b. A minus iota b. So this is Z bar, that is a minus iota b. This is the conjugate of the complex number. For example, if we have a complex number Z is equal to 1 plus iota, then z bar is equal to 1 minus iota. That is the conjugate of z is equal to 1 plus iota is 1 minus iota. Let us define the another term that is related to the same concept, that is the complex number, that is known as the modulus. Modulus of complex number. The modulus of complex number is denoted by mod of z. That is equal to square root of a real part square plus imaginary part of the complex number square, which is equal to square root of, as we know here, the real part of the complex number is a, that is equal to a square plus b square. So, if we find the modulus here, the conjugate, the modulus of, this is the modulus of z, if we see here the modulus of complex number z conjugate here, if we write here the modulus, as we know that the modulus of complex number is real part of square plus imaginary part of square. Here the real part is a, that is a square, plus the imaginary part is minus b, which is same as square root of a square plus b square. So the modulus of complex number z is root of a square plus b square, and the modulus of the conjugate is same as root of a square plus b square. Thus we can say here modulus of z is equal to modulus of z conjugate. Let's do some examples related to the same concept. Let's take the example number first. Say example number first is we have to find the real part, imaginary part, conjugate, and the modulus. Find the real part, imaginary part, and the modulus of the complex number z is equal to, say z1 here is equal to 1 plus I. So the given complex number is z1 is equal to 1 plus I. We have to find the real part, then you have to write Re of z. Real part of z is 1. And imaginary part of the complex number, that is 1. Also we have to find the conjugate of the complex number. So z1 bar, you have to just change the sign of the imaginary part. Here the sign is plus, then z conjugate is 1 minus I. And the modulus of z1, that is equal to square root of imaginary real part, that is 1 square plus imaginary part 1 square, which is equal to root 2. So if we find here the modulus of z1 bar also, this is equal to square root of 1 square plus minus 1 square, which is same as root 2. So this is the real part of the complex number, imaginary part of the complex number, and this is the modulus of complex number, and this is the modulus of conjugate of the complex number. Now if we have a complex number z is equal to a plus ib, now we have to find the multiplicative inverse. This is the new term here, multiplicative inverse of z. So multiplicative inverse of z, that is z is equal to a plus iota b. Its multiplicative inverse is denoted by z power minus 1, which is equal to 1 upon z. So this is equal to 1 divided by, as we know that z is here a plus ib. A plus ib. So we write here z inverse is equal to a plus ib. We will rationalize here by its conjugate, that is a minus ib divided by a minus ib. This is equal to a minus ib divided by, this is a plus b, a minus b, this is equal to a square minus b square, which is equal to a square minus iota b square, which is equal to a minus ib divided by a square plus b square. Now, as we know that a minus ib, this is the conjugate of the complex number. So, here z bar is equal to a minus ib. So, we can directly write here a minus ib as z bar divided by a square plus b square. If we find the modulus of this complex number, that is modulus of z, which is equal to square root of a square plus b square. Thus we can say here modulus of z square is equal to a square plus b square. So for a square plus b square, we write here modulus of z square. So the direct formula is to find the multiplicative inverse of any complex number, that is z inverse, which is equal to z conjugate divided by modulus of z square. Let's do some examples related to the same concept. Let's take example number first. Find multiplicative inverse of the complex number z is equal to 1 plus 2i. We have to find the multiplicative inverse of this complex number. So the given complex number is z is equal to 1 plus 2i, and we know that the multiplicative inverse of any complex number is denoted by z power minus 1. So put here the direct formula, z inverse is equal to mod z conjugate divided by mod z square. So thus we have to find the only two terms, that is the conjugate of the complex number and the modulus of the complex number. Here the modulus of the complex number is square root of 1 square plus 2 square, which is square root of 5, and the conjugate of the complex number is 1 minus 2 iota. So z inverse is equal to, z conjugate is 1 minus 2 iota divided by square root of 5. So this is equal to 1 divided by square root of 5 minus 2 divided by square root of 5 iota. So this is the multiplicative inverse of this complex number. If we see here, z inverse is again a complex number. This is also of the form of a plus iota b. Let us define the operations of complex number. First, addition of complex numbers. If we have two complex numbers, say z1 is equal to a plus iota b and z2 is equal to c plus iota d. If we have two complex numbers, then we have to add. So z1 plus z2, which is equal to a plus iota b plus c plus iota d. You have to directly add the real part of the complex numbers and the imaginary part of the complex numbers. So this is a plus c plus iota b plus d. For example, if we have a complex number z1 is equal to 1 plus 2 iota and z2 is equal to 3 plus 4 iota, you have to add these two complex numbers. So z1 plus z2 is equal to 1 plus 2 iota plus 3 plus 4 iota, which is 1 plus 3 plus iota times 2 plus 4, which is equal to 4 plus 6 iota. So this is the addition of two complex numbers. Now second one is the difference of two complex numbers, or in other words we can say the subtraction of two complex numbers, subtraction of complex numbers. In the same here, if we have a complex number, this Z1 and Z2, we have to difference these two complex numbers or subtract, say Z1 minus Z2. That is equal to A plus iota B minus C plus iota D, which is equal to A minus C plus iota times B minus D. You have to subtract the real parts of the complex numbers and the subtraction of imaginary part of the complex numbers. For example, we have a complex number Z1 and Z2 here. We will subtract these two numbers, Z1 minus Z2, that is 1 plus 2i minus 3 plus 4i, which is 1 minus 3 plus iota times 2 minus 4, which is equal to minus 2 minus 2i. So this is the procedure how to subtract the two complex numbers and how to add the two complex numbers. Now third one is multiplication. Multiplication of complex numbers. So how to multiply the complex numbers? If we have a Z1, say A plus IB, and Z2, C plus ID, we have to multiply these two complex numbers. So Z1 into Z2, which is A plus IB, C plus ID. By actual multiplication here, A into C plus A iota D plus iota BC. As iota square, as we know that from the previous class, iota square is equal to minus 1. So minus BD. This can be written as AC minus BD plus iota times AD plus BC. For example, if we have to multiply the complex number here, Z1 is equal to 1 plus I and Z2 is equal to 2 plus I. We have to find the Z1 into Z2, means we have to multiply these two complex numbers. So 1 plus I, 2 plus I. You can use the direct formula here, or you can solve this by actual multiplication. That is 1 into 2 plus I plus iota into 2 plus I. This is 2 plus I plus 2I minus 1. Same iota into iota square, that is minus 1, which is 2 minus 1 is 1 plus 3I. So this is the procedure how to multiply the two complex numbers. Now fourth one is the division of complex numbers. Division of complex numbers. How to divide two complex numbers in this? Say if we have a complex number Z1 is equal to A plus IB, Z2 is equal to C plus ID. We have to divide, say we have to find Z1 divided by Z2, which is equal to A plus IB divided by C plus ID. To divide these two complex numbers, you have to solve this expression. We will rationalization here by its denominator. That is A plus IB divided by C plus ID. We will rationalization here C minus ID divided by C minus ID. By actual multiplication here, A plus IB into C minus ID. This is A plus B, A minus B formula. This is equal to A square plus B square. Here the value of this is equal to C square plus D square. So multiply here, this is AC minus A iota D plus iota BC plus BD. Plus minus is minus and iota into iota is iota square which is minus, so that is why there is the plus c square plus d square, which is equal to, collect the real parts, AC plus BD, AC plus VD plus iota times AD plus BD divided by c square plus d square. That is equal to AC plus BD plus iota times AD plus BC divided by c square plus d square. This is the procedure how to divide the two complex numbers. Let's do example related to the division of complex numbers. Let's do an example related to the division of complex number. For example, we have a Z1, 1 plus I, and Z2, 1 minus I. We have to find Z1 divided by Z2. So Z1 divided by Z2 is 1 plus I divided by 1 minus I. So rationalization here, 1 plus I divided by 1 plus I. This is equal to 1 plus I whole square divided by 1 square plus 1 square, which is 1 minus 1 plus 2i using the identity a plus b whole square divided by 2 is equal to 2 iota by 2, which is I. Now, let's define two more terms here. If we have a complex number a plus ib, z is equal to a plus ib. If b is equal to 0 here, means imaginary part of the complex number is 0. Thus we can say here z is equal to a is purely real. If a is equal to 0, then z is equal to ib is purely imaginary. So, if we see this question at the last here, this is I. This is purely imaginary. Thus, we can say the division of these two complex numbers, z1 divided by z2, is purely imaginary because the real part is 0. Let us do some important examples related to the same concepts. Example number 1, z1 minus z2, z2 into z2, z1 inverse, z1 into z1 conjugate, modulus of z1, modulus of z2, modulus of z1 plus z2, z1 z2 conjugate. Real part of z1, real part of z1 plus z2, imaginary part of z1 z1 conjugate. If z1 is equal to 1 plus I, z2 is equal to 1 plus 2i. So we have to find z1 plus z2, z1 minus z2. So first part here, z1 plus z2. So z1 plus z2 is 1 plus I plus 1 plus 2i, which is equal to 1 plus 1 is 2 plus 3i. Second part is z1 minus z2. z1 minus z2 is 1 plus I minus 1 plus 2i. This is 0 minus I, which is minus I. And third one is Z1 into Z2, Z1 into Z2, which is 1 plus I into 1 plus 2I, which is 1 plus 2I plus I minus 2, which is minus 1 plus 3I. And multiplicative inverse of Z1, fourth one, Z power minus 1. As we know that this is Z1 conjugate divided by modulus of Z1 square. Z1 conjugate is 1 minus I divided by 2, because it is modulus is square root 2, which is 2, which is equal to 1 by 2 minus 1 by 2I. Modulus of Z1, sixth, this is the part number 5th, modulus of Z1 is equal to root 2. Modulus of Z2, this is the I part, modulus of Z2, this is root 1 square plus 2 square, this is 5. Z1 into Z2 whole conjugate, Z1, Z2, this is this, Z1 into Z2, so Z1, Z2 whole conjugate is minus 1 minus 3I. A real part of Z1, so real part of Z1 here, what is the real part of Z1? That is 1. Imaginary part of, real part of Z1 plus Z2, Z1 plus Z2, its real part is 2, so a real part of Z1 plus Z2 is 2. Imaginary part of Z1 into Z2, so imaginary part of Z1 into Z2, imaginary part of Z1 into Z2 is 3. Now let us define the term integral powers of iota. So what are the integral powers of iota? As we know that iota is equal to square root of minus 1. So iota power 1 is same as iota. Iota power 2, this is equal to iota into iota, that is root of minus 1 into root of minus 1, that is minus 1. Iota power cube, that is iota square into iota, which is minus 1 into iota, that is minus iota. Iota power 4, that is equal to iota square into iota square, as iota square is minus 1 into minus 1, this is plus 1. And iota power 5, if we solve this like iota power 4 into iota, this is 1, this is iota. In the same way, iota power 6, this is iota power 5 into iota, that is minus iota. No, this is iota 4 into iota square, this is 1 into minus 1, that is minus 1. So repeating the same process here, increasing the powers of iota here, this is iota power 1, this is iota power, this is minus 1, this is minus iota 1. Again, the value is iota. Same, iota is minus 1. If we find the value of iota power 7, this is iota power 6 into iota. Iota power 6 is minus 1, that is minus iota, which is this. So, after the interval of 4, we get the same values of the powers of the iota. Thus, we can say the period of the iota is 4. In general, we can say here, iota raised to power 4 q plus r, that is equal to iota raised to power r. That is, you have to remember only the 4 values of iota, iota power 1, iota power 2, iota power 3 and iota power 4. For example, if you had to find the value of iota power 26, you can break this like iota 4 into 6 plus 2, here the r is 2, you can write iota power 2, as we know that iota power 2 is minus 1. Thus we can say iota power 26 is equal to minus 1. In the same way, if you have to find the value of iota raised to power 121, the value will be in these 4, means either you will get 1, -1 iota or minus iota. So you can break here, iota raised to power 4 into 30, that is 120 plus 1. This is iota. So iota raised to power 121 is iota. So you can apply the formula this for any power of the iota, you will get the value of the iota. Now let's learn another concept related to the concept of iota. That is 4 consecutive, this is the consecutive here, 4 consecutive sum of powers of iota. So let's take the example here, iota power 1 plus iota power 2 plus iota power 3 plus iota power 4. Here this is the consecutive powers of iota here. As we know that iota power 1 is iota, this is -1, this is -I, and this is 1. So the result is 0. Let's take another example, that is iota power 21 plus iota power 22 plus iota power 23 plus iota power 24. So iota power 21 is iota, iota power 22 is iota square, which is -1, iota power 23 is -I, and this is +1. Again the result is 0. Now if we do this example, say iota power 101 plus iota power 102 plus iota power 103 plus iota power 104. Yes, these are the integral powers, consecutive powers of iota. 101, 102, 103, 104. Thus directly we can put here 0. So the sum of these powers is iota power 101, iota power 102 till iota power 104, the result is 0. Now remark, if the iota is in denominator, then it is better to take this iota in numerator. What I mean here, if you have to find the value of 1 plus I. It is standard position is 1 by I, you have to rationalization this. I divided by -1, this is -I. 1 by I and -I is the same, but it is better to write -I here. It is better to remove the iota from the denominator. That is, if you have to find the value of any complex number 1 plus 2i, then definitely you have to rationalization this. If you rationalization this by its denominator, definitely iota will free from the denominator. That is all for the today's lecture. Thank you very much.